Hello everybody, and I just wanted to do a quick recording here on how to use the Visual Studio Debugger on a Windows machine. So to get right into it, here is a basic program that I've thrown together, and it's just a simple struct. It has a constructor that immediately prints out that it's been created, and a destructor saying that the object's been destroyed. This program just has a simple pointer, which will be the address holder for my class objects that we create in memory. There's a for loop here that's going to be assigning new values of new objects that we're allocating onto the heap, and then assigning those addresses, the locations of where those new arrays are living, to the pointer here. And then we have that pointer's object that's pointing to being deleted and deallocated. So sometimes we get confused on like where we allocate things and where we deallocate things with our dynamic memory, or just really anytime dealing with pointers. So this is kind of a cool technique for just how to figure out if I have a memory leak. That's a concept we get introduced to in 10B and C, but how do we really know? So I'm going to comment these things out right here. This is probably some really bad memory management. We're instantiating objects and we're never deleting them. So this will definitely induce a memory leak. And we'll run the debugger and see the tools and how it works. But before we get into the advanced tools of looking at memory allocation, I just want to go over the debugger really quick. These little dots right here that I'm introducing are called breakpoints. And these are where the program is going to stop executing as I run it. So if I go up here to debug, I can do start debugging, or I can do start without debugging. I'm going to do start debugging. The program right now is running through, it's building. I have a console now. And there we go. Nothing's happening here. And I see that I have a little yellow arrow right here in the program. So this means that we are technically right here where my cursor is, just before the line of the for loop. That is where the program is stopped right now. And up here, I have some tools in my toolbar. If you don't have these, you can simply right click in the upper portion of Visual Studio, and there's a whole plethora of different menus that you can have. I really don't mess with too many, but I do use debug, and that's where you're going to find these different little options right here. And so we have a few different things we can do. We can restart the program, stop debugging the program, which effectively just shuts down. My console will stop running, and we're really just done for the day until I restart it again. Let's say that there was a function call. I hit step into right here. It'll actually go into that function, and then I'll actually be in another place in the program. So if I do step into, nothing really much is happening except, oh, there it goes. I stepped into the instantiation of these objects, and it actually went into my class. And now it's inside of my constructor. So that's an example of how to use step into. Alternatively, I could just use step over. And if I hit it, you'll see that the yellow arrow down there just keeps going line over line over line over line. And that's just how you can kind of just go through the program line by line by line, is using the step over key, which is really helpful. Other times, you don't want to go through line by line, but you want to get to like a certain phase of the program. Like this thing is going to run 1,000 times. I don't want to do step over 1,000 times. So I'm going to remove my breakpoint right there. And I'm just going to hit continue. And what this will do is it'll just run until it hits another breakpoint. So I hit continue. We're constructing a ton of objects. Going, going, going. Going strong here. And we've reached the end. So elapsed time, 15 seconds, and here's my little yellow arrow. The program's still running. We haven't gotten to the part where it gives like the usual blurb at the end of the console. And that's because we just hit continue until it got to the stop. If I hit continue again, there's no more breakpoints. So it just stops. And then there we go, we got the usual blurb of stuff at the bottom. So that's how you use breakpoints. It's how you use just the debugger in general to step over, step into. Really great tool for just to figure out what's actually happening in the system line by line by line. Another tool for the debugger is to look down here into your, it's called the autos or the locals window. And this right here shows values that are in your local scope. So right now I have a variable I and a pointer PT. PT is pointing literally at nothing. It's filled with just junk. That's a junk address because I didn't initialize it. It's just pointing to just garbage right now. But instead of having it instantiate with garbage, I'm going to instantiate it with null pointer. Let's restart the program and see if that changes anything. And I hit step over, and there we go. So instead of pointer pointing to 0xCCCCC, it's actually pointing at null. It's literally pointing at nothing. So you're being very explicit about what it's pointing at, which is helpful. So I'm just going to keep that like that. You'll notice that this also turned red. So my breakpoint was right here, and then I hit step over, so it went to the next line. So we're at line 15 now. And because there was a change between line 13 and line 15 to this specific variable, it turned red to tell me like, hey, pointer is now pointing at null pointer. Kind of helpful. We're going to see the same thing happen to I. Our local variable here, I, is going to be instantiated, and it's going to be given a value. So if I hit step over, it's now 0. It's red, and it told me like, hey, and I is now 0. And as we keep stepping over, new things keep getting assigned to pointer. I keeps getting incremented. We see that change is happening throughout this as I keep just tapping the step over key. So that's some basics on how to use the locals, how to look at what values are in the program. I could even hover my cursor over the variable in the window and I can see that I is 6. Pointer is pointing to 0x0106, all that junk right there. So you can just hover over things and it'll actually tell you the local value in memory at that moment of execution. So back to our main topic, how do we find a memory leak? So you're going to have to change some settings in here, and you're going to have to go to address level debugging. So if you just type address here into your search window and you see where it says enable address level debugging, if you click on that, I already have my box checked, but you'll have to select that. And that's what's going to let you be able to look at memory and also be able to look at memory allocation. So mine's set and I'm going to hit OK. So right now the program is running. I'm going to restart it and get a fresh look. So program, we're at line 13. I'm now going to open up some menus here. So these are a few menus that I find really useful, diagnostic tools, and also this heap profiling tool. So I'm going to click on heap profiling, and I'm going to take a snapshot. What this does is it looks at how many objects right now are on the heap. So right now I have 0 objects. I've instantiated nothing, so my allocations are 0, and my heap size is 0. Outstanding. I'm also going to put a breakpoint right here at the line where I'm going to be creating new objects of new instantiations of the my class object and putting them on the heap. So if I hit continue, I am now at line 17, and I'm going to take another snapshot. Still nothing's happened. I've allocated nothing to the to the heap, and my heap allocation is at 0 kilobytes. So that's what we expect, because technically I'm at line 17, but I'm actually like right here. I haven't executed that line, so nothing's happened on line 17. But if I hit continue, the program has run, the for loop has incremented, as you can see here with the 1, and I've created new objects. So this is red down here in my locals, and so is the I. That's also red in locals. So what's happened? If I take another snapshot, I see that I have allocated 4 objects to the heap. And that makes sense because my class object, if I count in the computer science way, I have 0, 1, 2, 3. I'm counting on my fingers here, but 0, 1, 2, 3, that's 4 objects. And that has now been allocated to the heap. And now pointer, if I hover over it, it's holding the address to that newly instantiated my class object. And it's 4 wide. Awesome. So I've allocated that to the heap. I'm going to hit continue again. So now we can see that the for loop has incremented through once more. I have a new address that pointer is pointing to. And so that last address I had, I don't have access to that anymore. And so that's an abandoned child. And that's how you get your memory leaks. Because now I can't, whatever it was pointing to, when increment I was 1, I can't get to that anymore. That's lost and gone forever. Hence our leak. So if I take another snapshot, yeah, I've allocated some more objects here. And we're going to keep continuing to allocate objects. So this is going to go 1,000 times. And I'm going to delete this break right here. And I'm just going to let this run. I'm going to let it keep incrementing, let it keep allocating objects to the heap. And then we can check what happened at the end of the program. So I'm going to hit continue here. And this thing's just running along, cruising. A few things are happening. It's just constructing, not destructing. That's bad. And then over here, this bar was climbing. So I had 904 kilobytes to the stack. Sorry, I keep saying stack. This is the heap allocations. 932 kilobytes to the heap and 956 kilobytes to the heap. So we're constantly adding to the heap in memory. And if I take another snapshot, I allocated another 1,000 objects, and that's 41 kilobytes. And that's just in a few seconds. That was 9 seconds of execution. So if this program is to run for like an hour, I mean, this is going to eat through your RAM eventually to where you have nothing left to work with. And the program is just about to exit. I'm right here next to the return. So this could definitely lead to some problems. So instead of creating these dangling pointers, just another name for them, I am going to instantiate an object and I'm going to delete it for science. So let us restart the program. Got the console. My program is right here. Now the key is to, when you're doing your heap profiling, you're taking your snapshots, make sure that you take a snapshot pretty early in the program before the action really gets going to get a baseline. Because what these snapshots do is they check the difference from the first snapshot. So if I only snapshotted at the very, very end, there'd be no difference to check. So I got to take one really early and then one at the very end. So I'll take a snapshot. For some reason, I got 197 allocations. And if I take another snapshot, I get +0. So that's the delta, the change between snapshot 1 and 2. So this is maybe just my baseline for the program just to even operate. So I'm going to hit continue. And now it's running, and this looks pretty good. We're creating objects, we're destroying objects 3 at a time, and cruising right along. All right, we're at the very end of the program. We constructed and then we deconstructed. Let us take another snapshot. So this is great. I allocated 1,000 objects to the heap, and then I deallocated 1,000 objects to the heap. So it looks like I got actually one additional object that was allocated that I left dangling somewhere in the program. But the key here is that I had 197 allocations before this for loop, and now I have 198 allocations after that for loop. So my delta is 1. So that means that I created 1,000 objects, and I deleted 1,000 objects between lines 15 and 19. So that's how you want to properly deallocate all of your memory. And so this is just a cool tool to use to make sure that, yeah, I did have that many objects. I ran it, and now my delta is low to nothing. And here's, I'd say, acceptably low. One other thing to note is that we can actually look at what pointers are looking at in memory. So I'm going to restart the program. And the program has to be running. So right now, my little arrow is here. My console is empty. I'm effectively running the program in debug mode. I can step over, I can step into, I can do all of those things because we're actually running. In this window, if I go to debug, Windows, I go down to memory, I have another little menu here. So this isn't like memory stick 1, 2, 3, 4, and if you only had 2 sticks of RAM in your computer, it wouldn't be just 1 and 2. What these are is just the number of windows that you want to look at. Let's say you're messing around with a binary search tree, and each tree has 2 nodes in it. You could have memory 1 looking at node 1, and memory 2 looking at node 2. And you could have memory 3 looking at a different pointer, and memory 4 looking at a different variable. So these are just however many windows you would like to have open. That's what you can look at. And this is RAM right here. Scrolling up and down right now, you can see all the different addresses and what's there. So right now it's just totally full of junk, and that's what we'd expect. Random access memory is just, it's got what it's got. Maybe if I ran a different huge program, I'd see maybe some artifacts of what I had run prior, but in this case, I do not. So this is a peek into the RAM module of our computer. So how does that help us? Well, we can look at this pointer right here. So this pointer is in memory. As the compiler saw pointer at line 13, this went into memory and it allocated enough room to hold a pointer for a myClass object. So this pointer, which is just a container for an address, it lives in our memory already. So if I go to my memory module, go to address, and I use the ampersand memory operator, I type in pointer, pt, I hit enter, and it takes me to where my pointer is in memory. So anytime that I assign a new address to this pointer, it's going to go to this place in memory of my RAM, and it's going to insert that address here. That's what's actually storing. And then if it was like perhaps maybe like a string, it was a name, it would say the name right here in my output in this column here, but this is in a way that's not human readable, and that's fine. So we just get a little bit of junk. So how is this useful? I can keep an eye on this place in the RAM, which is my pointer object, and I can see how it's changing throughout the execution of the program. So if I hit step over, something just happened. My pointer was loaded all the way with CCCCCC, but now it's loaded with null. In my locals, I see the red change, and then in my RAM module, I see that there's a red change. So that just means that something's changed. And like I said, if you maybe were dealing with a binary search tree and the node was pointing to something useful, you'd actually see like, okay, there's a value there, and you'd be able to track those changes. But in this case, we're just modifying what that pointer is pointing to. So I'm going to keep executing by hitting step over. And every single time I step over, it's getting loaded with a new address because it's pointing to a different place in memory. And it just keeps on changing and changing and changing. But this is a great tool to keep track of how your program is behaving. Great way to check how you're allocating and deallocating memory. And if anybody has any questions, feel free to hit me up on Discord. And I hope you find this useful. Happy debugging, and I'll see you all in the next one.